So we are back to recording. Um, Here is what our chapter 1 is going to look like. We are going to spend the rest of this week and most of next week on chapter 1. Right? Again, if you have friends in other Chem 030 or Chem 131 classes, they may have already finished chapter 1 by now. Right? So they're not doing any, again, of this sort of groundwork here. So what we're going to start with in chapter 1 is we're going to start with a whole lot of definitions, a whole lot of some new vocabulary, and then we're going to come back to significant figures, and then eventually into dimensional analysis. But if we can get to significant figures today, that is good for us. That's what we need to be. That's where we need to be. Okay. All right. So hopefully the next couple slides will be super boring. It's super easy. There should be a lot of review there. What we're going to do though is we're going to try and do the activity that we couldn't do on our very first day of class because we weren't there in person. And that is to think about what it means to be chemical or non-chemical, things made of chemicals and things not made of chemicals. So what I'm going to do is I'm going to give you an object. And in the chat box, if you could put either a C or an N, C for chemical, N for non-chemical. And we'll see how we do with these. How about a cloud? Okay. So we had a little bit of both. We both got both chemical and non-chemical. Anybody want to defend their choices? Anybody want to say why they put chemical or non-chemical? I'm gonna be quiet. How about we do a couple more? Maybe we'll be brave then. How about a blueberry? All right. How about oxygen? Oh, that was very fast. That was a very quick response on oxygen, that it was a chemical. Why was that one so much easier to decide on?
Because it's like, you know, we already know that it's like on the periodic table and stuff, so it's obviously,
Oh,
gonna be
all right.
chemical.
All right. So if it's on the periodic table, it's a chemical. Yeah. Okay. What if it's made of things that are on the periodic table? Does that make it chemical or non-chemical? Oh. So I'm seeing a lot of things like, well, if it's made of stuff that's a chemical, if it's made of elements, made of atoms, it's chemical. All right. So do we want to rethink our answer to a blueberry? Is a blueberry chemical or non-chemical? It is definitely chemical, right? How about a cloud? Mhm. How about a bunny? All of those things that we've got, yeah, they're all made of chemicals, right? How about what have I got there? How about a rainbow? Mhm. Wow. Seeing a lot of non-chemicals for that one. A few chemicals, right? So what is a rainbow? What is it made of? Oh, so it's just made of light, right? Is light on the periodic table? It is not, right? Right. So it's just made of energy. Light is just another form of energy, right? So that would be non-chemical. How about something like DNA for all my biology folks out there? Definitely chemical, right? Right? It's a part of us, right? Might be natural, but it's also chemical. How about sunshine? Chemical? Hmm, absolutely. Good. How about a burrito? Yeah. So what this is kind of hopefully pointing out to you is that we have some baggage when it comes to these words chemical and non-chemical. Our first instinct is, oh, if it's natural, it must be non-chemical, and that's not quite true, right? So the way we're using words in our class might be different or might have different connotations than the way you use the very same word in another situation. We're going to see lots of that today and all throughout the semester, where we have a very particular word that we're using in a very specific way that may have a broader meaning or a more narrow meaning, depending on how we're using it in our class. Um, so let me show you this. This is my favorite sign. It's an actual sign. I used to live out in Colorado, in Durango. This is a chemical-free park. What do we think of this sign? What is in this park? If there are no chemicals in this park? Are there trees? Right, right. But if it's chemical free, trees are made of what? Carbon and wood and all those things that are made up of atoms, right? So if it's chemical free, truly chemical free, there's gonna be no trees in this park. All right. Are there going to be air? Yeah. Yes. Yes, Brenda. There'll be nothing there, right? There'll be absolutely nothing there, right? Right. There might be a rainbow, but that's about it. It's going to be hard to breathe because there's not going to be any oxygen there, right? It's a pretty sad little park, is what I think. So again, this is a real life example of the way we use the word chemical free is not the way we're using it in our class, right? So when we say chemical free, sort of out, like if you're out shopping, right? What they're meaning is very specific types of chemicals, right? So maybe even specifically synthetic ones, things that are made in a lab, as opposed to that same chemical found in nature. So again, just let's just kind of use this exercise as an opportunity to sort of just be aware that we are using our words very carefully, right? They have very specific meanings in the context of chemistry, which may be really different from the way they're used out in the world of marketing or consumer products. Wow. Oops. Goodness. Hello. Not sure why that decided to show up right now. All right. Let us move all of you off to the side there. Okay. Why is this not moving? There we go. All right. So let's go back to what then is matter? What are those things that are made of chemicals? How do we know that they're different? Right? Those are things that have mass, right? They're made of stuff. They're made of atoms, right? Those are our building blocks there. Um, and they take up space, right? They occupy three-dimensional space, right? So if we had a box, we could, measure its length and its width and its height, and figure out what its volume is. Or if we had some weird shaped object that didn't sort of have a nice geometric shape, we could find its volume in a different way by looking at how it displaced a liquid. We're actually going to do both of those in our lab Should we ever be on campus again, we will be doing those in our lab, hopefully next week. That'll be our plan. All right. So anything that you can find that is made up of atoms, right, has mass, and it occupies some volume. All right. And we know that that matter comes in sort of three main ways, right? I truly hope this is not new information to anybody, right? But what I do like about this is the way the information is presented, right? So this is one way you can sort of reframe information as you're doing your reading, right? Or as you're reviewing your notes. It's a way to show the relationship between things. That's what all those arrows are going back and forth between them. We've got the use of color coding, right? So everything about the solid is in red, everything about the liquids in blue, everything about gases are in green, right? So you're using color again as a key or sort of a visual cue. It's got words that tell you how they're the same or how they're different. And then again, those arrows are showing the relationships. How do I get from one to the other? Right. So I'm guessing out of those 6 words for the different ways to go between solid, liquid, and gas, the different phases or different states of matter, that you're familiar with probably at least 4 of them, right? There's a few that you might not have heard before. Um, but freezing and melting, right? Those are the two opposite but related matters, right? When things go from a liquid to a solid, it's freezing. And when they go from a solid to a liquid, it's called melting, which hopefully will happen soon with our snow. We have similar conversion between liquid and gas, right? Things can be vaporized or boiled. Right. That's our common word for that. Things going from liquid to gas is boiling or vaporizing. And then going in the other direction. When our gas turns back into a liquid, it condenses, right? It kind of comes together and you can see those water droplets forming for water. The one we're probably less familiar with is going from solid to a gas or gas to a solid, right? We don't see that very often. Water doesn't do that. It's one of our more common materials. So we just don't experience it as often. But there are some objects, some materials that go directly from a solid to a gas without ever turning into a liquid. So dry ice, right? If you've heard of dry ice, it's called dry for a reason. It doesn't go through that liquid phase. That's just carbon dioxide. It goes from a solid form to a gas form directly. And then deposition would be the other direction, going directly from a gas to a solid without ever passing through a liquid. Okay. So we're going to, again, use some of this vocabulary later on. And we're going to talk about things being solid, liquid, or gas. The other nice thing about this particular way of organizing it, right? So it's got a ton of information on there, but it's all in one place. That's what I like about it. You've also got sort of that molecular view or that atomic sized view of what the different particles would look like. So you can see in a solid how the atoms, right, those little balls are very close together, right, practically touching, versus in a liquid where they're sort of next to each other, but they're not really organized. And then with the gases, they're just sort of all over the place, bouncing around their container. So again, hopefully not really new information there for you. All right. So here are maybe some words that we haven't thought about, or again, a couple of these words are things that we're going to use in a very specific way here. For example, that word pure, right? We have in our head what that means, right? And we kind of make a moral judgment almost about it, right? But that's not what it means here, right? So when we're talking about how to organize matter, how do we talk about it, right? We could sort materials into solid, liquid, and gas. But we know from that little triangle we just saw that they can be converted, right? We can take things that are solids and melt them and turn them liquid. So that's probably not the best way to organize material. This way that we've got here, which is one of my favorite pictures from your textbook, organizes matter based on what it's made of. How is it put together, right? Which is going to be a little more useful for us. So we'll start on the pure side, right? So that's the side over there on the left, and talk about that. So we've got sort of that first distinction. So all matter is at the top, and then that matter can be either a mixture or a pure substance, right? So let's look at what we mean by a pure substance. That doesn't mean it lives a holy life, right? That just means that it's made of only one kind of material, right? That's what we mean by pure, right? It has nothing to do with whether it's all natural or good for you or bad for you, right? Pure substances are made of one kind of material. Mixtures made of more than one kind of material, right? And within our pure substances, we can sort of further break them down. So this kind of a diagram is showing you sort of the hierarchy or how things are fitting within bigger categories, right? So our pure substances can be either elements. There's 120 elements. That's it. Those are the ones on the periodic table. Right? If it's not on the periodic table, it's not an element. It is that simple. Elements are made of only one kind of atom, right? So when we look at it real small, right, that's what that picture at the very bottom is, at the very bottom left. That is a picture of what copper looks like, right? If we could shrink ourselves down and walk among the atoms, it's only one kind of atom. It's the same one kind of atom all the way through for copper. So copper is an element. Copper is also a pure substance. Right? Another kind of pure substance is a compound, and this one's a little trickier, right? So something like sugar, right? If we could walk around sugar, right, get inside that sugar crystal, we would see these little molecules of sugar, right? But they're all the same, right? They're made of those same atoms in the same order hooked together, right? So all of those molecules look the same. They're all made of the same different kinds of atoms, whatever the little white, black, and red atoms are. They're all the same. Excuse me. Excuse me. Every one of those molecules looks just like the neighboring molecule, right? And they're different from other kinds of molecules for different compounds, right? So our compound, even though it's made up of different kinds of elements together, right? They're put together in such a way that they come in these little bundles that are always the same with each other, right? So those red atoms and white atoms and black atoms are bonded together, right? They don't come apart, right? They're stuck together. They're completely together and they stay in that shape and in that structure. And that's what gives sugar its properties. That's what makes it sweet, is the way that it's put together with the particular atoms in the particular shape. Okay? But that's still a pure substance. It's still considered a pure substance because within that sugar, every single one of those molecules is identical. All right. Question, Pauline, go ahead.
So, can compounds be separated or are they just stuck like that?
So they can be separated only chemically, right? So if we separated the compounds, we would have to actually break those connections between the red atoms and the white atoms and the black atoms. We could separate them, but we would have to do something chemical to them. We would have to break those sort of bonds that hold them together. If we separated it only physically, right, kind of went in there and sorted with just our fingers, we're not going to be able to break apart those molecules. We would be able to separate it into this sugar molecule and that sugar molecule and that sugar molecule, but we would still have sugar. Yeah. So that's the difference between separating something physically, right, sort of just without breaking any of those connections, and separating something chemically, which would require breaking those bonds down. Mhm. So elements, right, while we're on that topic, elements, right, we can't break them down physically or chemically into anything else, right? No matter how we sort out an element, we're always just going to get that same one atom, one kind of atom back out. We can't separate them into other new materials. Okay, good. So, okay. Mixtures, everything else. Mixtures are made of more than one kind of material. So it could be mixtures of elements, it could be mixtures of compounds, it could be mixtures of an element and a compound. It can have two things, it can have three things, it can have 112 things. No real limit to it, right? Mixtures can have really any proportion of those things, right? If you think about it, right? If you're trying to make chocolate milk out of your chocolate syrup and your milk, right? You can mix them in any proportion you want. You can make it mostly chocolate syrup and a little bit of milk, or mostly milk and a little bit of chocolate syrup. It can vary, right? But if you're going to make sugar, right, a compound, it always has to be the same number and the same kind of red atoms and black atoms and white atoms. Okay. Was there a question? Did I miss a hand up a little earlier? Okay. Awesome. All right. So our mixtures have variable composition, right? And because they're mixtures, right? If you think about it, if you just took a bunch of I don't know, like different colored jelly beans, you could physically separate them, right? You can go in there and sort them out, right? Without breaking any chemical bonds or doing anything drastic to them. You could separate out the different colors. And that's what's different about mixtures. Mixtures can be separated physically back into their components and their original um, compounds or elements that made them up. Whereas pure substances can't be separated physically into anything new, only chemically broken down further. All right. So we've got two different kinds of mixtures, right? And basically there's one there in common words, right? They either look the same all throughout or they don't look the same all throughout, right? So they're either smooth or they're chunky. Um, and the science words for that are homogeneous, right? That means homo means the same, right? So it looks the same all throughout. So that little cup of tea there looks the same all throughout, right? It doesn't, I don't think it has little chunks of anything in it, right? It's not clear at one part and dark in the other, right? There's no tea leaves floating in there. But tea is definitely a mixture. There's lots of different components. Depending on what kind of tea you have, it's going to have different proportions of different kinds of parts of the tea plant or of the tea leaf. You may have put sugar in your tea or not. You may have put cream in your tea or not. But it's definitely all the same throughout. So whether your first sip and your last sip, right, contain the same relative amounts of them. If we physically separate our tea back into the water and all the other compounds that make it up, sure, right? If we boiled it, all the water would evaporate and we'd be left with, right, a bunch of little brown crud at the bottom, which would be all the other components that are in our tea. So we could physically separate, right, those materials. We haven't changed what they are. We haven't broken any bonds. But we have, again, kind of taken a different look at them. Heterogeneous is like the example way on the right there. And that's our classic example of oil and water, right? So if you've ever tried to make Italian dressing, right, if you leave it sit, right, it'll eventually separate back out into the water component and the oil component, right? There's going to be regions where it looks like water and regions where it looks like oil, right? So that little sort of molecular picture down there shows you how sort of all the water parts are staying at the bottom there. That's the clear part at the bottom. And all the oil parts are made up of oil kind of molecules and they're staying on their own side, right? They're not uniformly mixed throughout. They're not homogeneous. They're heterogeneous, right? So hetero is our prefix. That means different. So it's going to have regions or spaces within that object or that material that are one kind of mixture or material, one kind of substance, and another region where it's made of a different kind of material. Okay. All right. So mixtures, variable composition, they can be separated physically into their original components. Pure substances made of only one kind of material. They cannot be physically separated into anything new, but they can be, compounds at least, can be chemically broken down back into those elements. Okay. So those are possibly some of our newer things. What I want to give you a chance to do is to spend just a few minutes. Here are the 4 new words that we just did. See if you can take a minute or two and just jot down, right, a definition or a feature. How would you decide, right? So if you had to decide if something was an element, a compound, a homogeneous mixture or heterogeneous mixture, how would you tell them apart? let's take a minute here to, right? What's also always helpful is, can you give an example of each of them, right? Preferably one that we didn't already talk about.
Is helium one?
Is helium one what? Which category do you want to put it in?
An element?
It is an element. Yes, it is. It is on our periodic table. He is number 2 on our periodic table. So yes, helium would be a good example of that, right? What are the features of an element, right? Well, one, it's on the periodic table. That's pretty easy, right? Right. But it's made of only, right? Elements are made of only one kind of material and only one kind of atom. We cannot break it down physically or chemically into anything else. Yes, a heterogeneous, I like that. I like Camilla, that's a good example. Heterogeneous mixture is when each compound stays in their own space. Yeah, or each group of compounds, right? There could be a collection of them that all hang out on one side versus another. Right, but it's definitely made of different things, right? And also that proportion of the different things can change, right? So you can make your Italian dressing with more of the water component or more of the oil component. It's still considered Italian dressing, even though there's a slight variation in that composition. With a compound, it can't vary, right? The number of atoms of each kind have to stay the same, and they're bound together. All right. So each of these has typically more than one. Yeah. Yeah. Homogeneous is when they mix all together, right? Like coffee and milk. Perfect. Yeah. So each of these categories has more, there's more than just one feature that you're looking for. There's usually a collection of things that we're looking for, right? So this kind of a chart is good when we've got sort of all these new words like we had right now, to kind of compare them. You can kind of see what's the same about them and what's different. If you'll notice when I did this, I made sure that I had sort of the same feature that we talked about in each of them, right? I've got all the pure substances on the top, all the mixtures on the bottom, right? And the first bullet point for all of them talks about what they look like, right? So an element, because it's made of only one kind of thing, is going to look uniform throughout. A compound also is going to look uniform throughout. A homogeneous mixture is going to look the same all throughout, right? A heterogeneous mixture does not look the same all throughout, right? So just knowing if it's uniform looking, right, just taking a visual look at it isn't enough to decide uniquely what category it's in. You've got to think about the other bullet points, right? So the second bullet point is, right, what are the elements made of? What are the compounds made of, right? How are the mixtures have variable composition? That's all the second bullet point. The third and fourth bullet point talks about how they can be separated or not. Right. So that's one way of kind of sort of structuring your information to sort of easily sort of compare and contrast so that you can make a distinction and decide, well, what kind of a compound or what kind of a material really do I have? Do I have a mixture? Do I have a pure substance? Is it homogeneous, heterogeneous, element, or compound? So that is what our activity, again on Friday, when our learning activity will have us do this. All right. The two that are the most challenging to tell apart are compound and a homogeneous mixture, right? Because they have a lot of things that are similar, but some essential differences. So I made one more chart here, right? So this is a good kind of chart to do when you've got two things that are kind of overlapping, like compound and homogeneous mixture. They have a lot in common, but there's some key differences there. So you can look at this chart and you can see that I've underlined the words that are different, right? Again, they're grouped. The first one's talking about what's combining. So in a compound, we're combining elements, right? Chemically. right? Or compounds. We're combining them chemically. They're bound together versus just in a mixture where they're just sharing space, right? Like our coffee and our cream, right? We're not making anything new out of our coffee and cream. They're not forming a new material. You can still very clearly taste the coffee and very clearly taste the cream. They maintain all their original and unique properties, right? They're just sharing space in that homogeneous mixture. Versus in a compound, right? When two things come together and form a new material, new combinations of those atoms and elements and compounds, they're going to have different properties. A compound always has the same composition, definite composition. A mixture can have variable composition. I can put a lot of cream in my coffee or a little bit. Right? It's still coffee in my cream. A compound we can only separate chemically. We have to actually break those bonds to separate out the different atoms that are in our compound. Whereas in a homogeneous mixture, we can physically separate them again. We can do something that separates them without turning them into a new material. Okay. And lastly, some good examples of each of them so we can kind of think about them. So wine, air, right? Air is a good one. It's a good homogeneous mixture. It's made of lots of different kinds of gases, right? But lucky for us, right? The oxygen is not all in one side of the room. That would make it hard to breathe, right? So it's uniformly kind of distributed all throughout. Some examples of compounds over there on the left, right? Sodium bicarbonate, sugar, carbon dioxide, vitamin C, right? Those are all the same, right? Every sample of vitamin C, no matter where we get it from, always made of the same kind of atoms in the same order, right? To give us those properties that are vitamin C. Right? Makes it good for us. Alrighty. Questions on those? So again, in your portfolio, you get a chance to kind of practice with those definitions, that pure versus mixture kind of distinction, and then between those four different kinds of subcategories: element, compound, homogeneous mixture, and heterogeneous mixture. All right. Just to kind of, we've talked about, I mean, we've used this word, how to separate things physically, right? And you might think, well, how do I do that? Here are some different physical kind of things we can do that would let us separate things. In fact, a couple of these we use in recycling for sorting out the different materials in that recycling. You know, in the county, right, we kind of throw all our stuff in one bin, and then they're separated out. So how do they do that, right? It's not, there's not someone there manually sorting out your plastic from your metal, from your glass. But density is one way we can do it. Some things float and some things don't float. So by putting all of our mixtures of our recyclables in a big pile of water, right? Some of the plastics are going to float, and we're going to be able to scoop those off the top. Our glass is going to sink to the bottom, right? And we'll be able to collect those from the bottom. Magnetism, right? We can separate out some of our metals from it that way. Did anybody make coffee this morning? Yeah, you did a whole bunch of these this morning then, right? If anybody made coffee, right? If you used a coffee filter, right? Then you use size, right? You use size as a way of separating out the grains, right? The little grounds of your coffee from, right? The liquid that went through. The liquid passed through that, right? Had smaller particles than the bigger grounds, which stayed behind. You use solubility to actually make the coffee. When the hot water goes through the grounds, parts of those coffee beans dissolve in the water and parts of it don't dissolve in the water, right? And the part that does dissolve in the water is what makes our coffee super delicious. That's our solubility there. The last one is separating by mass over there. Anybody eat cookies over their keyboard? I can't be the only one, right? You know how it gets crumbs in your keyboard, right? What do you do to get rid of them? Right? Well, I know what I do is I pick up my keyboard and I blow on it, right? Right? that's separating it by mass, right? Or brushing it away. That is separating it by mass, right? The lighter particles, the crumbs, right, fall away, but the heavier things, the keyboard stays in place, right? When I blow on my keyboard, the keyboard doesn't go flying across the room, just the crumbs and the dust that are on there, right? We do these things all the time. We just don't necessarily maybe call them by their fancy science names there. But these are different things we can do. So adsorption is absorbing onto a surface, and absorption is sort of drawing something into. So yeah, adsorption is one of our physical separation techniques. If you dye clothes or you really even dye your hair too, that's kind of what you're doing. You're doing it's a physical change. Okay, good. Awesome. Other questions on that? So we have a few more definitions before we get back to the numbers. All right. So we've used this word. I always hate when I use a word before we define what that is. But we said physical properties, and we've used that word, but we haven't really given it a good definition yet. And in fact, chemical physical properties and changes, it's going to be one of those things we work on tomorrow in our lab. Assuming we can get into lab. That's what we'll be working on tomorrow. That's one of our things we'll be ready to do. So physical properties. These are properties or characteristics of a substance that we can observe, right? Measure, observe, somehow look at without changing that substance into anything else, right? It sort of has those features all by itself. A good rule of thumb is, can I detect it with my 5 senses, right? Any of those things, right? Can I see it? Can I hear it? Right? What does it smell like? What does it taste like? What does it feel like? What is its texture? Right? Usually any of our 5 senses are things that we're going to be able to detect a physical property with, right? In order to determine that property, we don't have to turn that object into anything else. Right? It's itself. We can just look at that object all by itself. Right? Let's compare that with something else, right? Different color, right? Sort of a comparing kind of thing. It's still a property, it's still a characteristic of that material, but it's chemical in nature, right? So that's different, right? So physical has to do with what that material is and does and looks like without changing. Chemical properties are going to be, well, what are those features or those characteristics of that material when it does change or when it does combine with something else, right? So those properties are usually going to require more than just your senses. You're going to have to be combining that material of interest with something else, right? So if you look at those examples, you can see they're all having to do with things changing, right? So iron rusting, the fact that it rusts and other things don't, right? That's a chemical property. The fact that helium is inert, that it doesn't react with anything, right? So we've tried to put it with other things and it just doesn't seem to do anything. Or we can do a sort of a comparison. One thing is more reactive than another, right? All of those observations, all of those determinations of those chemical properties involve turning that material into something else. So that's our distinction between physical properties and chemical properties. Okay. Right. We have 2 other kinds of properties. Intensive, right, which could be both physical or chemical. Intensive properties. And then let's put the other one up here at the same time. Extensive properties. Okay. So intensive. Let's think about that in, right? That's a property that has to do with what that material is, the nature of that material, its identity, right? It doesn't depend on how much of it we have, right? So it's strictly a function of what is that material, how is it put together, right? So some properties like that, density, that's a big one. That's the one we're going to deal with in our lab next week. Temperature, color, those things don't matter how much of the material you have, right? If you think about it, right? Doesn't matter whether you've got a little cup of water or a big cup of water. If it's boiling, it's at that boiling temperature of water, right? Density of an object doesn't matter whether you've got a big piece of it or a little piece of it. right? The density, the proportion of mass to volume is going to be the same as long as it's the same material. That's intensive, depends on the inside or the identity of that material. Extensive, well, that's the opposite, right? That's outer, right? So I like to think of it the extent of the material you have. These properties depend on how much you have, right? So these are easy to think about. These are some of the things that we're going to measure, right? Mass, volume, size, right? Length, width, height, all of those things. Those all depend on how big of a piece, right? How much of that stuff we are measuring. So heat, how much energy is in something, which is not the same as temperature. That depends on how much of it we have, right? If you think about it, right? If you had a nice little kitty that was going to keep you warm, right? It's whatever the temperature of kitty cat says, right? That's going to keep you warm for a little bit. But if you had a giant tiger at the same temperature, that would keep you a lot warmer, wouldn't it? That's got more heat in it. They're at the same temperature, the little kitty and the big tiger, right? But the heat, the amount of energy in it, is smaller for the kitty and bigger for the tiger. I don't advise sleeping with tigers, though. That's probably not a good plan. Just get a heated blanket or more little cats rather than the tiger. What that means in terms of these properties, like, well, why do we even care about this? Right? So extensive properties are a lot of the things we can measure, right? Intensive properties are the things that if we can figure out what they are, we can use it to identify something, right? So intensive properties are going to be good for identifying what we have. Extensive properties are going to be good for telling me the how much. Okay? So as we get deeper into our labs, we're going to see how we measure some of extensive properties and relate it to some intensive properties to figure out what an unknown might be. Okay. All right. And then this is what our lab is going to be on: physical changes and chemical changes. So not too different from physical properties and chemical properties, except these are the changes, right? So these are processes. These are events that happen, right? So a physical change is a process or some alteration that happened, but the material didn't change composition, right? Whatever it was before, it's still that material, but in a different form or phase or state of matter. Again, involves just that one material, right? So any of those phase changes we had on our little triangle from very early on, those are all related to physical kinds of changes, right? Anything that changes its shape or state of matter, right? Compare that to the other side, right? The other side is chemical changes. So these are processes that do change what that material is made of. And again, usually involves at least two things getting together to have that change. So when iron rusts, that change going from iron to rusted iron, that's a chemical change, right? We've made a new material, right? It's not iron anymore. It's rust, right? Which is iron oxide. We've made some new materials, right? When we blow things up, right? When we set off an explosion, right? We've changed the material in that explosive into something else, right? Into lots of gas or lots of energy. Photosynthesis, for a more mild version, right? That's that plant having a chemical change happen. It's taking that carbon dioxide and water and turning it into plant parts, sugars or fruits or whatever that plant is all about growing. So we've got some nice examples, right? So physical means the substance is not changing its composition, and chemical, the substance is changing its chemical composition, or whatever it's made out of, right? So it's changing. We're forming something new with a chemical change. Physical, nothing new. It's just kind of a slightly different form. All right. Do we have questions on that? All right. Okay, so in our last few minutes, we're going to get started on significant figures, sort of counting them, and we'll take a look at some of the rules for them. Okay. So we're gonna skip our little frog for the minute, just so that we can have a little bit of this under our belts before we head off for the day. Okay, so let's look at this. There are actually two kinds of numbers in the world, right? Again, in the regular world, you're like, well, there's just numbers and that's all there is to it. In chemistry, we have different kinds of numbers. We have numbers that we measure, and we have numbers that are exact, right? And this all comes down to how well do we know something, right? So for science, right, as we measure things quantitatively, we need to know, well, how well do we know that, right? Right? How fine of a measurement is that? Is that true at all levels of measurement or just, sort of roughly? So we have exact numbers, which are numbers that don't have any uncertainty in them, right? So counting, right? We assume we can count, right? We can count how many students are here in this Zoom session with us, right? It's either, right? There's either 20 or they're 19, right? There's not maybe 19 and a half, right? It doesn't work that way, right? Counting gives us an exact number or a definition, right? There's no uncertainty. If I tell you there's 12 inches in a foot, there are 12 inches in a foot. Right? There's no uncertainty there. It's not maybe a little more than 12 or maybe a little less than 12. That's from a definition. Or geometry, right? So some of our geometric equations, like the area of a triangle is 1/2 times the base times the height. That too, in the 1/2 part, that's an exact number. It's not maybe a little bigger or a little smaller, right? But all of our measurements, all of them have some uncertainty in them, right? There's going to be we're going to have a limited ability to know what that measurement is. And it's going to depend on the tool that we use to measure it with, right? So if you look at that chart at the top, we've got the same numbers, right, in all of them. But on the exact number side, they're from the source of those numbers are from counting or a definition. On the measured number size, somebody had to actually go and get those objects and put them on a scale or measure their volume or their mass in some way. So 23 pounds of apples, right? There's a limit to how well we measure that, right? There's some uncertainty there, right? It might be a little more than 23. It might be a little less than 23 pounds, right? There's a limit. Depends on what kind of equipment we use to measure it, right? If we used a piece of equipment that measured it with way more precision, right? Maybe we would know it's 23.15 pounds of apples, right? But based on whatever equipment was used to measure these ones, we only know it as well as 23 pounds of apples, okay? Same with the 12 liters of soda or the 2.54 grams. Somebody measured those, right? And was limited based on their piece of equipment that they used as to how well, right? How many digits are we going to have in that measurement versus the exact numbers? Those numbers, again, there's no uncertainty there. They are what they are. We counted, or those are definitions of what those items mean. So that's what our significant figures are. They're all the digits that we know from measuring something that we know for sure, plus one digit that we estimate, right? So all pieces of equipment have little markings for us to read, right? So we know when we're between markings, we know for sure we're more than one but less than the other. And then we'll estimate in between, right? To know kind of, roughly where we are between that. That's as well as we can do, right? We don't get to estimate a whole lot of digits in between those markings, right? So there's a limit, right? Every measurement has a limit, right? We've gotten better at making that limit smaller, right? So we can know things more and more precisely, but no measurement is known exactly, right? So we want to be real careful with how we use that word exact. We use it differently in our everyday lives than we use it here. Exact has a pretty particular meaning as far as where some of our numbers that we're going to use come from. All right, so let us reiterate this. All measurements have limits. No measurements are exact, right? We might know them really well. We might have a lot of digits in them, but they're not exact, right? It depends on what tool we use, right? So when we go into lab to do measurements, there's going to be a different answer to how many digits should I have. It depends on what equipment we use, right? So how fine or how many of those digits, how well we know them, how well we know that value is the precision. And the number of significant figures tells us, right? If we have more significant figures, it means we had a more precise measurement. Okay. Let's work on counting them. Actually, let's just watch this video together, and then we'll call it a day after this one. So this little video here is going to remind us of all the things we need to know for counting significant figures and the rules for adding and subtracting and multiplying them. So it's just a couple minutes long here.
Looking at the news. There are so many things to from all sides. There is at the beginning. There's the middle. There's the place and that's the no. There's a exam. The zero plus the end. You got it is a top there. The end.
Can you tell me if the sound is okay for you?
The sound is choppy. Like I can't.
Okay.
Yeah.
Okay. Let's skip that then. It is linked on Blackboard, so you can go back and get it. I will tell you, this is one of the things I hear students humming to themselves when they're taking their quizzes and things. So it's like I said, it's only like 2 or 3 minutes long, but we don't want to annoy you all with the sound if it's not going to be clear. Let's just try practicing for the last few minutes here then. Let's try and see if we can figure out how many significant figures are in these numbers, right? So zero, it's the zeros that are troublesome, right? So zeros at the beginning, never significant. Zeros in the middle, always significant. Zeros at the end, it depends. If there's a decimal, then the zeros at the end are significant. Without a decimal, then none of the zeros at the end are significant. All right. So let's start with a 3.67, right? So you can use our chat box again. And how many significant figures are in 3.67? Right, good. That was not too bad, right? There's no zeros in it. Okay, how about the second one? 3.67 times 10 to the third. Yeah. Also 3, right? That times 10 to the, right? Remember scientific notation. That times 10 is just telling you where to put the decimal point. It has nothing to do with how well you did the measurement. So scientific notation is really easy. It's a nice way to show significant figures because all the significant figures are in that first part. Okay, how about 3.670 times 10 to the third? Right. See how easy that was to tell? If we had written those out, it would have been really hard to see whether that zero was going to be significant or not. All right. How about 0.3067? How many significant figures are in that one? Right. Good. So that zero at the beginning, not significant. It's just kind of there so you can find the decimal point. But that zero in the middle is significant. Okay. The last one in the first row, 0.0067. Okay. So now we're going to have a fight. We've got 2s and 4s. All right. All right. So remember, zeros at the beginning are not significant. It doesn't matter if there's a decimal point or not. So all 3 of those zeros right at the beginning, not significant. Only the 6 and the 7 are significant there, right? In fact, if you put that in scientific notation, all of those zeros at the beginning would just disappear. It would be 6.7 times 10 to the minus 3, right? So sometimes, like I said, it's easier to tell significant figures in scientific notation, okay? So that one at the bottom there, right? Leading zeros are not significant because they're just there to show you and kind of help hold that decimal place, right? They're not necessarily anything that was measured, right? So they're just telling you that the size of this object or measurement is very small. Yeah, so leading zeros, not, yes, they are a placeholder. They're not significant digits, okay? But something like this next one in the second column, 1.0067, how many significant figures are in that one? Yeah, see, that one has 5. That means we measured the one, we measured the next position, the 10th place, it just happened to be 0, right? The 100th place happened to be 0, right? And we kept measuring, right? So that one does have 5. Yeah, so those zeros aren't just placeholders, they're actually part of the measurement. All right, 1.00 times 10 to the 2. All right, good. Yeah, 3 significant figures, right? Those zeros at the end after the decimal 1.00, those are significant. That decimal point says, hey, I measured it. Those zeros are good to go. All right, so let's really compare that down here. We have 5,400 with no decimal place. Good. That one only has 2 significant figures, right? Because there's no decimal. The zeros at the end are, again, they're just there to show how big that number is, right? To show the difference between 54 and 5,400, right? They're not, we didn't actually do any measurements in that range, right? But what if I put a little dot there? If I put 5,400 and then a decimal point? Yeah, that little dot makes a difference. That means I measured not just the thousands and the hundreds, but I also measured the tens and the ones. They just happen to be zeros, right? So that's a different level of measurement, right? To the calculator doesn't care. Calculator doesn't care. Math people don't care. Chemists, we're gonna care, right? That's unfamiliar for us. What about this one at the bottom? What's going on down there? The very last one there. Yeah. We don't usually see this very often with a little underline there, but that underline is for the last significant digit. That's a way to show that one of those zeros is significant, but one of them isn't, right? Because if we don't put a decimal, none of them are significant. If we do put a decimal, they're all significant. You're like, well, how can I show that just one of them is significant? Well, we can underline it like that, or you could put it in scientific notation. 5.40 times 10 to the third. That would show 3 significant figures. It'd be the same size, still the same size value, right? But it more clearly shows the number of significant figures, right? So that's how scientific notation can help us out with all of those weird zeros at the end there. Okay. Other questions on counting significant figures before we head out for the day? Okay. So we didn't get quite as far as we wanted to, but that's fine. So we will pick up either on Thursday or on Friday, depending on where we are, with the rest of our work on significant figures. And eventually we'll get to dimensional analysis, and hopefully some of our lab work, whether we're in person or not. So please keep an eye out for any announcements from the college, and from me. I obviously I'm not having office hours because we're not there. But I am going to be available. I can answer emails, or we can set up appointments, or I can hang out for a little bit after today and we can get all that squared away. Anything else?